Namaste. Good morning, guys. This is the second video on the topic of momentum, and so I just wanted to go into it a little bit more. All right. So if we take a look at the board, let's discuss this a little bit further because you can go. This is kind of an important topic, and you can go into it a bit more. And there's something I find interesting. I think that I want to show you about it. So momentum is the concept that objects have this property if they have mass, when they're moving, this property that Isaac Newton called momentum, and this property factors into collisions. When things collide, momentum goes from one object into another object, and we say that it can transfer, and it depends on your mass, and it depends on how fast you're going. Okay, kind of like kinetic energy, but slightly different. And forces cause momentum to change in an object. If you don't have any momentum, you exert a force on an object, an unbalanced force on the object, the force will give the object momentum. Momentum is also conserved. All right. So in a collision, when two objects collide, in that system, we call that a system when they collide and they interact. The momentum between the two objects is conserved. Now, it may go from one object to another, but the total momentum that was there before the collision is equal to the total momentum that there is there after the collision. Okay, so there you have that. Now, you might be looking at. I put in the slides. I got some, there's some weird pictures in there, and one is Bruce Lee, and the other is Muhammad Ali, and these are two heroes of mine from when I was a child in the 1970s. Bruce Lee was a martial artist, very famous martial artist, and why would I have a picture of momentum, or why would I have a picture of him in the notes that I made on momentum? Well, it's because Bruce Lee, being a martial artist, used to hit people. That's what the martial arts is, and there's an art form in doing that. And he was not a big guy, so he did something. He was able to do something like completely amazing. And if we were in class, we'd be watching the video on this. In fact, I'll probably post the video on Classroom so you can watch it. Where he would do, he was able to generate so much momentum in a punch that he was able to knock an average sized grown man legitimately down with a punch from 1 inch away. He used to train at doing this, and he used to use the tips of his fingers too, and put his whole body into this tiny 1 inch of motion that he was able to knock an average sized man down with a punch from 1 inch away. Why? Because he generated so much speed. He wasn't a big guy, so he made up for it with lightning fast speed. So his punches had a lot of momentum. All right. Muhammad Ali, there's a picture of Muhammad Ali up there. In fact, there's a picture of Muhammad Ali and George Foreman fighting in a famous boxing match from the 1970s called the Rumble in the Jungle, where Muhammad Ali tried to, and did, wound up getting the heavyweight title back from George Foreman, who currently held it at that time. And so why would I have a picture of those two guys up there? Because like the two rounds I showed you, the AK-47 and the M16, all right, the two men, like those rounds, are a study in momentum. The two fighters. George Foreman had a lot of momentum because he was just huge. He's a huge, muscular guy. So his punches had a lot of momentum because he had this big ham of a fist that if you got in the way of, would just give you all of its momentum and knock you right out. But he was slower. Muhammad Ali was a smaller man. He was still a big guy, but he was smaller than George Foreman. And he, like Bruce Lee, made up for that lack of size or that size disadvantage with lightning speed. Muhammad Ali his punches are very, very fast, and it's all about momentum transfer. So that's where that's why those guys are examples of this concept called momentum. Now, there's something else I want to talk to you about. Now, momentum, that's the how you calculate it as a quantity, but in a relationship with force, it goes back to Newton's second law, which is a net force on an object, right, is equal to a change in momentum over time. Okay, and really it's a change in time, but we'll say that we'll start at time is 0 always, so we'll just write a t there. Okay, now remember I've been trying to teach you guys all year to speak math. So what we're going to do is we're going to just look at this equation a little bit differently. I'm just going to rearrange it. All right, so what I'm going to do is I'm going to take the t and multiply it on both sides right there. It's going to cancel there, and it's going to go onto this side right here by the force variable, and I'm going to rearrange it just because I like it better this way. All right. All right, and now I'm going to read this equation and slightly interpret it, because like I said, this is not a math class. We use math, but we interpret it. It has meaning. It's not just some random equation, y equals mx plus b. All right, this is a this is a set of ideas. And what does this equation say? How does it read? Well, what it says is that a force over time, acting over time on an object, causes that object to change its momentum. Okay, and that's how we read it. Now, physicists have given this particular term, when you rearrange Newton's second law to look like this, we've given this particular term right here a name, and we call it impulse. Okay, and we say that an impulse on an object changes its momentum. Okay, and what does that mean? Well, it actually has some practical applications in the real world. Okay, if you've ever tried to catch a baseball, all right, especially like a pop fly that's being hit, from out there by the batter and it makes it all the way out to like center field, for example, and you're going to catch that thing. How are you taught to catch a baseball? And I'm trying to do this on the small screen, but you're taught to reach up to it, grab it, and pull it in. Why? Well, because if you do the reverse, if you're just like trying to catch that baseball, all right, just like stand there and not give it all, that would really hurt. Right? The ball has a lot of momentum and it's going to give it to you, all right, one way or the other. So what happens is what you're doing is when you catch the ball, you're exerting a force on it and you're taking away its momentum. Remember, taking away can be a change also, right? Giving something is a change, taking away is a change, all right, in the object's state. And so one way to do it, the reason why this works, or why it's better to catch it through reaching, is because you're going to change that object's momentum either with a large force over a short amount of time, and you're going to feel that. You can stop that ball instantaneously, okay, if you lock your arm up, but it's going to hurt. Why? Because you just exerted a large force on that ball in a short amount of time. That ball just stopped really short. And since you exert a large force on the ball, the third law says it's going to exert a large force on you, on your hand, and you're probably going to hurt your hand, okay? The other way to change the momentum of the ball, all right, is to exert a smaller force over a longer amount of time. It doesn't hurt, okay? So you reach out when the ball's up here, you grab it, you're starting to exert the force to stop it, to take away its momentum out here, and you drag it out over time, and that allows for a much more gentler stop of the ball, and it's just easier to catch that way, and it doesn't hurt, and so on and so forth. So that's why that works. So momentum works this way. All right. This is also the theory behind, and this is actually an important thing, the airbag in your car. God forbid you're ever in an accident. And why does an airbag work? Well, when you're in an accident, your body has momentum because it's moving. You're in the car, you have mass, you have velocity with the car, and there's velocity and momentum. And you're going to go forward because of the first law, because you have inertia. And so you're going to stop one of two ways. Either your head is going to stop very instantaneously by hitting the dashboard, and that's like stopping the baseball instantaneously, and that's bad because it'll stop, but in order to stop your head short, it's got to exert a large force on your head, okay, which will probably cause brain damage or maybe kill you, okay? Or if you can stretch out that stopping of your head, your body, your head in particular, over time, you can do it with a smaller force, and that's what the airbag does. When the car senses that there's been collision, the airbag comes out instantaneously as the car is still crashing. And so it touches your face, and it starts the collision, it starts the force on your head sooner, and your head still goes forward, okay, but it takes longer. The airbag causes it to take longer to do that. So the time went up. So the of the collision went up. So the force exerted on your head went down. Okay. So kind of like that to just blow this up a little bit. All right. You can either stop by using a short amount of time, so a little amount of time, and a large force. Or you can stop something, change its momentum by exerting a larger time and a smaller force. And in many cases, especially in a case where you're going to get hurt, this is much more optimal. This is also the theory behind any packaging that we do. We have packages coming to our house like every day, every other day from Amazon or whatever, all the things we order. And you notice all the packaging, they have those plastic, bubbles in there. What do? Well, they change the nature of the collision. When a package is dropped, that's a collision. There's a momentum exchange in there. And you're trying not to break whatever the heck is in the box. So the way you do it, what you do is you put those plastic bubbles in there, and they allow, when the collision happens, a kind of giving effect, so that it stretches the collision out for the object in the box, stretches the time out, and a smaller force is required to stop the object that's in the box, and it doesn't break. Okay, so that's the concept of impulse. So I'm going to give you guys some problems, all right, that will have not just momentum conservation in there. Now remember, there's two versions of momentum type problems. There's the conservation problem, m1v1 plus m2v2 is equal to m1v1 prime running on a board space plus m2v2 prime, okay? And this is the recoil problem. It's the elastic, inelastic collision problem. There's that version. The other version of a momentum problem deals with the impulse version, right? Where you have a force acting over time, changing the object's momentum. And to stretch this out, all right, may look like this. So force times time is equal to m1, all right, v1, actually m1 v1 prime minus m1 v, or just v1, all right? So you would get a problem like this, or you would use this version. Let me just use a quick example. And I'll just come up with one off the top of my head. All right, you might have one that looks like this. So let's say that we have a rocket, which I'm going to draw the world's crappiest rocket, okay, like that. It has fins on it and fire, so you know it's a rocket, all right? And so what's happening is, let's say that this rocket is at rest, so V is 0, and then we're going to burn the engines, okay? And what we want to know is, okay, so here we're going to burn the engines, and let's say that we're going to burn the engines for 10 seconds, and the engines can generate a force of, let's say, 30 newtons, all right, and we'll give the mass of the rocket, and it's a small little rocket, so we'll have a mass of like 3 kilograms. And what we want to know is, after 10 seconds, how fast is that rock going to be going? So we want to know, all right, V prime, okay? Okay, well, we have forces. When you see a problem that has forces, velocities, and times in it, you probably want to go to this version of the momentum equation, all right? So let me do this out, okay? So let me rewrite that. Okay, so force times time, the impulse, is equal to mass of the rocket, we'll just call it M1, V prime minus, and why am I writing minus? Because that is the change is minus, okay? That's what it means in mathematics, okay? Y2 minus Y1, X2 minus X1, and so on. All right, M1 V V, which would be the original speed. Okay, so what's going on there? Well, it's at rest initially, so the original speed is going to be 0, so that term goes. All right, and I'm going to solve for that. So plugging in some numbers here, I have 30, okay, newtons times 10 seconds is equal to 3 kilograms times V prime. So what's V prime? Well, 30 times 10 is 300 is equal to 3 V prime. Divide by 3, in this case, divide by 3, that's going to go. And I have that V prime is 300 divided by 3. So the rocket will be going 100 meters per second at the end of 10 seconds. Okay? And if that's the case, then you could also find out the acceleration of the rocket too. If you knew both speeds and the time it took to change from one speed or the other, and you could go further. Okay, so anyway, I wanted to show you the impulse version of the equation. So again, if you have questions, and I'm sure you will, come and see me during the office hours, and I'll be looking forward to talking to you then. So, all right, so good luck on these, and remember to enjoy your apocalypse.